Okay, so our next speaker for today is Professor Winfried Hensinger. He's the head of the Sussex Ion Quantum Technology Group, and he's the director of the Sussex Centre for Quantum Technologies. Professor Hensinger is co-founder of Universal Quantum, a full stack quantum computing company, where he serves as chief scientist and chairman. At the University of Sussex, his group works on constructing a trapped ion quantum computer, demonstrator device, a quantum simulation engine, as well as portable quantum sensors in collaboration with a number of academic and industrial partners. His talk today will be on the future of the field in academia and industry. Thank you very much for being here today. We're really happy to have you. So please start whenever you're ready.
Great. Thank you very much for the invitation. I have to say, it's probably one of the hardest talks I've been asked to give. And so I'm going to give this my best shot. But obviously, predicting the future of a field is tremendously hard. And so I'll just have a bunch of thoughts. I find it much easier to give a talk about physics and so I'll give this my best shot. And I've made some slides to kind of maybe guide my train of thought. Also very happy to have questions and even questions during the talk. So please just ask. I don't know whether people can raise their hands or something, but yeah, do feel free to ask at any time. So let's see if I can share my screen. Good, that should work. Okay. So I think in order to do a reasonable job with doing something like that, it's maybe good to start with my personal journey, because in a way, when you try to interpolate something, it's good to learn about the data you use to do that. And so let me start with a one slide summarizing what I did and how I got here and where do I think, and use that as a basis to say where things are going. So I've started my undergrad in Germany. Is a very motivated undergrad physics student wanting to change the world, and was lucky enough to get a stipend to then do my master's in PhD in Australia, where I wanted to work on a particular topic, in fact demonstrating a new type of quantum effect. So that was still a phase where quantum computing was really, really far off, and where people focused on building or challenging quantum mechanics, looking for demonstrations of new quantum phenomena. And so I did my PhD, worked extremely hard, knowing that it's extremely hard to eventually get an academic position. And I always knew I wanted to do research. That was quite obvious for me in physics. And so I then spent 5 years in Australia, and half of that I spent at NIST in Gaithersburg, where I was lucky enough to work with a Nobel laureate, Bill Phillips, in fact, where we then demonstrated this new quantum phenomena called dynamical tunneling. During my PhD, I over lunch, I listened into conversations with one of my PhD advisors, a theorist called Gerard Milburn, who was one of the early theorists thinking about practical implementations of how we could build a quantum computer. And while that was very far away from my own PhD, I wanted to learn. I got really excited about it, because rather than just demonstrating quantum phenomena, it was about controlling them and actually doing useful and sensible things with them. And so over my PhD, I realized I will absolutely build a quantum computer. And so at the end of my PhD, there was a solid plan of me then trying to figure out what kind of physical platform would be the best in order to do exactly that. And So I moved eventually after really very carefully assessing all the different approaches of how you could build a quantum computer at the time. I moved to Chris Monroe's group at the University of Michigan, and where I felt his approach in building quantum computers would be probably the most likeliest to succeed. And so after working there for 3 years, I then was lucky enough I could offer a faculty position at Sussex, where I moved. So as you can see, one of the things in my career certainly probably like quite prominent is that's gone really from all lived on 3 different continents, 4 countries, and none of that was easy. In fact, it was extremely hard, and maybe that's a message I want to give to you guys. Don't think it's going to be easy. It's actually very hard, and everything about it is very hard. Every experiment you do will typically not succeed the first time around. People will tell you it's never going to work. And if you want to make it work anyway, you're going to have to be unbelievably persistent. And now coming back maybe to the mission of my talk. So when I decided in 2002 I wanted to build a quantum computer, most people didn't really believe it's possible. So it was more like one of these things you write into a grant application in order to prove that the rather fundamental quantum research actually has some kind of useful application. Yet, however, a few kind of mad people at the time, indeed, and I was one of them, did believe it's possible and worked really hard to make that happen. So, cutting a long story short, this is where I am right now in my personal journey. Now I'm in a true quantum superposition. So I'm a professor at the University of Sussex, leading a research group, a research center. In 50% of my time, the other 50% of my time I spent in a company with a simple or difficult mission, whatever you want to however you want to call it, to build a practical quantum computer. So this is where I've been coming from, and now maybe want to give you some kind of prediction where I think things are going to, or some of the things you can look out for. And when I started my career, the only way to do research in physics or research in quantum computing was within a university environment. There were no companies out there, and the only way to do this really exciting stuff was within a university environment. And there are a few starting points for quantum computing, but they're all in a university environment. So that was very, there was no other option available. And maybe that's something which is changing now is that there is a new type of physics career, and that's something really exciting. So quantum research for real, what does that mean? It means you can spend every day 8, 10, 12 hours to do research. And that is now not at a university, that's actually in a company. Because with the emergence of many of these quantum computing companies, we need a lot of people who do exactly that. Spend the time doing research in order to build these practical machines. And so one of the first real phase changes which have happened to the field is that research is not just confined to academia anymore, in fact, quite the opposite. So I would say it's actually a lot easier to do focused research in industry than it is in academia. And maybe let me quickly explain why. And so in the description of what the organizers wanted me to do, they wanted me to, because of my unique position of doing both, I wanted to kind of give you some kind of comparison of how these things have evolved or will evolve. And so let me tell you about my first 50%, and that is work in academia. So there's always these lovely memes where this is what other people think I do, and that's what I do, and whatever not. And I didn't quite have the time or skill to come up with beautiful pictures and do this, but would have loved to do that. But let me give you the benefits and opportunities to work in academia. And let me start with the challenges first. So lots and lots of administration. So running a big research group means you have to literally do everything to make that group work. Teaching is beautiful, but it takes a lot of time. And if you want to do it right, and if you want to do it well, it really takes a lot of your time. Universities, you may be surprised or not, can be a very inefficient entity. So because of the diversity of work carried out in the university and the multiplicity of tasks, that also means that the entity often is not streamlined for one thing, for example, for research. And that means like there's a lot of friction and a lot of things you're going to have to do to make it work. And I'm going to get to that in a second, but let me actually get to that right now. In order to be successful in the university, you would think you just have to be a good researcher or maybe a good skilled in teaching, but that's not true. There's plenty more things you have to do really good. You have to be an accountant. You have to be a health and safety specialist. You have to be a psychologist, a plumber, a negotiator, a repair specialist, a motivator, secretary, grant writer, and that's only the starting point. So all of these things you have to do. Nobody trains you ever for these things, but you have to do them really well because there's nobody else doing these things. And your research group will not succeed unless you do all of these things. Now, you'd think research is just amazing, and in university you can do these tremendously beautiful things, but in reality, in order to do anything sensible, you need funding. So in order to do research, you need equipment, consumables, people, and you need a lot of time to acquire funding for that. So you'd think it will be just about the merit of your ideas. A great idea will always attract funding. Unfortunately, that's not the case. There's plenty of good ideas and way too little research funding. And so a lot of times you write what you think is a fantastic proposal, but it just won't be funded. And also the type of proposals you typically write, they will be very small. And so your funding, the way you acquire funding is more like a drip feed, where you really like get funding in very small portions. You're gonna have to report for each of them. You're gonna have to renew each of them or start this again. And so this is hard. And now the next maybe point quite is obvious, and that is your work never ends. Like, so you you don't stop working at 6 o'clock and that's it, but you might receive an email at 10 p.m. and you need to react really quickly, and you need to do that. So job security is an interesting one. It's both a challenge in academia and a benefit. So basically there is a threshold point until job security is really hard in academia. So there's not as many faculty or permanent positions in academia. They're all faculty positions, and until you get to that point, you don't know for sure whether you'll ever get such a position. And if you're a postdoc or something, that obviously means like you don't know whether you're gonna get such a position, and that obviously means it's really a lot of pressure on you, and you really have to believe and love what you do in order to undergo all that pressure to go ahead. Right, so I've probably gotten now everybody of the idea of ever working in academia, but it's not quite as simple as that either. There's also a lot of benefits to work in academia, and one of these benefits is academic freedom. You can just explore anything you want. It's amazing. Like, if you find something fascinating and interesting, you can explore it, and it doesn't need to be necessarily useful or why. You don't even need to necessarily convince a lot of people about it. Like so, academic freedom is real, and there's really a lot you can do, which you could probably never do in industry. Listed teaching before was a challenge because of the time commitment, but it's also absolutely wonderful to be around students and to inspire students, to work with students. I love teaching. So I see it as an absolute fantastic benefit. The whole environment is inspiring. You're literally around amazing people and in an amazing environment where there's constant personal growth. You're always going to be a student. You're always going to learn. You learn from your students. You're going to learn from other researchers in the field. So it's absolutely wonderful. And what it also means is there's plenty of opportunity for collaboration. And because you're not in a commercial environment, you can openly talk about interesting things, and you can in a way open up, and you have the opportunity to work with the most amazing people from across the world, and I find this always unbelievably awesome. And so I remember I had the opportunity to work with Bill Phillips, who won a Nobel Prize. I endless hours in the corridor having fantastic discussions with him and many other fantastic scientists I was lucky enough to work with. So I think that's a huge benefit. There's lots of talent in universities, the ability to critically think, to send good research environment, and also job security. So what are the challenges in industry? Result driven rather than curiosity driven, and that can be sometimes very useful if your interest is exactly aligned with the mission of the company, but also sometimes it may also be you may not be able to do some type of research you'd want to do. There's commercial drivers rather than academic interest, and that means also that some constraint and obviously less academic freedom, or in principle no academic freedom. Now there's huge benefits of working in industry, especially in the emerging quantum computing sector, and that means you can have a focus on research. You can work with absolutely top talent, with the best engineers out there. We have sufficient funding to do the extremely difficult engineering properly. Like in a university environment, you'll never have enough funding. You're always going to have to cut corners or work in a second-class environment, because if you work with a foundry or something, no university can ever pay for that. You have a specialist for any task, so you're not like in a university environment. You don't have to necessarily do everything. You can do research. That means you can maybe do 8 or 12 hours a day of research, and you don't have to do all the other things. As long as your company is healthy, you're gonna have it. You do well, you're gonna have a job forever. And I think it's fantastic to have really professional project management. So I think that's kind of my feeling of where the benefits and maybe the future of both of these lies. You can see this is really novel. If I would have given this talk 10 years ago, I wouldn't have presented these slides, because only now in quantum computing these benefits in industry will apply, and that will get even stronger. So this is a very unique position you are, and in the future these benefits will become even more distinct, and so that's something where I think working in industry is a fantastic opportunity, and will only get better. We'll get a lot better. So now the question you might ask is what hardware you should be picking if you get into quantum computing. So there's obviously plenty of hardware platforms, from superconducting qubits, from photonics, trapped ions, neutral atoms, you name them, they exist, and there's people very enthusiastic about all of these. And so certainly we are in a phase where all of these platforms will be developed for quite some time. But the question then is, how are you going to make your personal pick? You're going to have to pick something, independent of whether you want to stay at a university or whether you go in a company. And my answer to you to that question is, ask yourself, can you make it happen? Do you believe in this approach? does that really take your fancy? Because if you can answer yes, I can build a quantum computer with that, then this is the platform you should pick. And maybe this is my personal recommendation for me to you. Ask that question: can you make it happen? After some very critical evaluation, can you make that happen? So that's what I would propose to you. So, but there's obviously the title of this talk is predict the future of the field, and so I felt like I need to have at least a graph in my talk, and so here you go. This is kind of how I would try to analyze all of this. So, so on my x-axis we have performance of a quantum computing, and on the x-axis, the y-axis performance, and the x-axis I've got time. So I'm gonna draw two thresholds in the performance. One, useful calculations that could be something in NISQ. I should say not many useful applications in the NIST domain have been found, but let's just keep that line somewhere. And then there's the obvious line that is fault tolerant operation of a quantum computer. And the big question is, and so now these lines correspond to these different platforms, and we all know, whoever you talk to, these platforms make constant improvement, and nobody argues about that. The nice thing is, across quantum computing, I think it's fair to say we're not in a position like fusion where it's always 10 years. All these platforms, even the worst performing ones, make constant progress and impressive progress at that. So the question now is, when do these platforms then meet these two thresholds, being useful calculations and fault tolerant operation? And so, I mean, I obviously would want to be on the red curve on platform 1, whatever that may be, and that's how I would try to pick. But on the other hand, platform 2 may also have some advantages, maybe much smaller, or maybe have certain performance advantages. So I think being in a style platform 2 line is just as good, like, you know, and I think if provided that platform 2 is not so much faster that the money will stop with platform 2, I think going in platform 2 is perfectly fine. Now the question is about platform 3. Platform 3 is some hardware platform which maybe is much behind platform 1 and 2. But there's obviously some kind of big promise, that maybe this thing is very small or super fast or has no errors or things like that. And the question is whether, with the speed of increase of that platform, whether people, and when I say people, I mean private investors or governments, are willing to pay for the development for such an extended amount of time that it will become a reality, especially once these other platforms have actually crossed the line of fault tolerant operation. And so that's maybe the question you need to ask yourself. So there's a risk in being in a platform 3 hardware platform, because that may be aborted at some stage. So that's maybe some guide to your thinking about how to engage. So what's the future of the field? I think it's fair to say there's exponential growth. So it's really the amount of people working in quantum computing and quantum technology is taken off like mad. We need more and more skilled people. There's a lot of investment being done. So it's really a fantastic time to be part of it. It's a new industry sector altogether. It's highly disruptive in its promise. That means that multiple industry sectors are really going to be transformed fundamentally by the applications once we've gotten a working machine. There's going to be a talent shortage for some time, so I think it's a good time for you to be in that field, because I think it's no question you will have a job if you're good and if you work hard. It's an opportunity to do results-driven research with the right means. Now, what I mean here, particularly in industry, but even universities have plenty of funding. So it's really great, and it's stark contrast to other fields where you have to build everything yourself and suffer from small funding. This is really a field where you can really have the means available. And for me personally, it will change the way we live. You might eventually be able to use these machines to create new pharmaceuticals, to do unbelievable things And for me, that's obviously maybe the primary motivation why I'm doing what I'm doing, because of the promise of the opportunities provided by this field. And so maybe I'm going to end this talk with maybe some kind of prediction of how a world with practical quantum computers will look like. So I think there will be applications in every industry sector. So quantum computer will be a machine you need to know about, and nearly any industry sector will use. But it's very much a parallel like to supercomputing, to current supercomputing. So we're going to use supercomputing for lots of different applications, but not for all of them. So there will always be a space for normal computers. Not every problem will be processed with a quantum computer. And the way you engage with quantum computers for a very long time is via the cloud. So you're not going to only own quantum computer, you will engage via the cloud. In terms of maybe the type of way quantum computers will change society, they will do that in a very disruptive way, similar to Google search algorithm. So where there is an application which can be realized, that will change the sector as is. And because of that highly disruptive character, I think there's also a strong question about ethics and regulation that will play an extremely important role. And that is something which will become more and more important, especially once quantum computers reach useful application. So this was my attempt to maybe give you a prediction of the field. I don't know how well I've done. Predicting the future is always unbelievably complicated. And so what I try to do is give you maybe an interpolation of what I have done, where I am, and where I believe things are going to go, to give you maybe some kind of justification why I'm saying what I'm saying. But let me end with just saying that the future is really in your hands. We need people like you in order to make and enable this fantastic promise of quantum computers. And so I want to encourage you to make the future with us and be part of this fantastic great question in building practical quantum computers. Thank you.
Thank you very much for your talk, and it was really insightful in answering a question that's really broad and really hard to answer for sure. But it was great to hear kind of your perspective on that. We have some questions for you. So the first one is, what technologies do you envision emerging from the pursuit of a quantum computer?
I'm certainly personally biased, and starting in 2000. Over the last few years, I'm strongly convinced that technology I'm working on, trapped ions, will build quantum computers, and we will build quantum computers. I have no doubt. I've always said this. When I started my group at Sussex in 2005, I had people rolling their eyes at me when I said it. Now a lot less people roll their eyes at me, and the result speaks for themselves. But there's other also very promising platforms, particularly in the domain of small qubit numbers, for example, superconducting qubits. Linear optics is a big question mark, the same like topological qubits. That could be very interesting, but a lot remains to be proven. But I would invite you to make your own judgment. Don't listen to just people who will want to in a way dictate your narrative. Follow this guide I've given you, and do the work yourself. Listen to people, but then do your own judgment. And I think that's the best way to really find what is the best platform according to your own judgment.
Of course, thank you. So the next question is from Thomas Clark. He says, fascinating discussion, Winfried, insightful as always. I was wondering what's the quantum volume you've achieved so far at Universal Quantum, and what are you most excited to achieve as a company / academic in the next 5 years?
So I'm limited of what I can say about some of the things we do in Universal Quantum, but the key thing, what distinguishes Universal Quantum from other companies is that we do not pursue a mission of say fighting with Google or IBM on the number of qubits or the quantum volume. And the reason why we don't do that, because if you were to follow such a linear path, you'd struggle to ever get to a point where you can really do fault-tolerant quantum computing with millions or actually billions of qubits. Now, we've published recently a paper in the research group where we showed that the shuttling-based approach, which we pursue, and you can look this up on, it's on a publication on our research group website, the quantum volume achievable via this approach compares unbelievably favorable to any other hardware platform. But to come back to what Universal Quantum is working on right now, we really focus on doing the engineering design to build quantum processors, so to build basically these fully electronic silicon quantum computing modules that scale to millions of qubits. And this is maybe where we are completely different to any other company. We do not attempt to distinguish ourselves in the NISQ domain. We truly trying to build million and billion qubit quantum computers.
Yeah, thank you. That sounds really exciting. I'm sure people will love to hear more about it tomorrow in the talk about universal quantum. So please look out for that. The next question, if you have time for a couple more, I know we're running over a little bit.
Absolutely, very, very much. Yeah.
Great. So this one is, what if quantum computers don't work or the money dries up? What part of the quantum industry should I position myself in to allow a good transfer to a normal computing company, for example?
I mean, I think, put it this way, there's certain hardware platforms which may just not get there, or if other platforms just get there first, the money will dry out, because eventually you have the question of, do you want a functioning quantum computer or do you want a promise or a pipe dream? And so on the other hand, I think some of the skills in quantum computing are transferable. So even if you work on one platform, it's not impossible to transfer to another platform. And it might be useful to pick your platform that you not in the one which works the slowest. There's plenty of transferable skills you learn in quantum computing. I mean, I can only really talk competently about eintrapping. There you do MEMS design, microprocessor engineering, artificial intelligence, machine learning, laser physics, theory, plumbing. So you name it, we'll do it. So I think there's no problem programming, software design. So there's plenty of skills you have. So I wouldn't think you'd have many problems with the skills you acquire. The money, I think, will always be challenging, but as long as the promise is there, I think, and we make good progress, I don't think it will dry up. And the good news is we are well beyond the point. Like in 2005, I had this discussion. I had many colleagues coming up to me and said, Winnie, I've got this thing now, and quantum computers will just never work. And we could have gone on the archive then, and there were all these papers out where smart people said they don't work because you're going to have all these cumulative errors and they will bungle up and it just doesn't work. But we had these amazing theorists who overcame every single one of these problems. We have now error correction. We have fantastic error correction. We have thresholds of 99%. 99% for an operation is not really that much. So progress always happens, but there's always problems will happen. And this is why we have smart people, smart theorists who then help us overcome these problems. So there are certain things, platforms where you have to beat some really fundamental physics challenges, and you may just never beat them or not on a foreseeable time. And so that's where that will come to an end. But there's other platforms which are so close, which cross every single threshold or every single tick mark individually, that you only now need to basically bring these all together, which also is a significant challenge. So I don't want to talk this down or say like we can do this immediately or very quickly. It's a long path, but I think it will happen. And I think we are now looking at all the results worldwide, and I'm very proudly proclaiming results from superconducting qubits, IBM, from all these fantastic companies who all demonstrate in their own platform that quantum computing is indeed possible. And I don't think we'll be in a position where there's a theorist coming up with a paper and saying fundamentally you can't have a quantum computer. but we're gonna have to work for these things very hard, and you know, whoever tells you 5 years is probably going to be 10 years. So that is certainly to be expected, and I think persistence is the key here. And you should not get into this field unless you have a lot of persistence.
Yeah. Okay. Thank you. That was a great answer. So we have some other questions, but if you don't mind, I'll put them in the Slack if you have time to look at that.
I haven't logged on the Slack, but yeah, I mean, I'm happy to answer a few more questions now or something.
Yeah, we have, I mean, a couple more minutes, and so there's two more. Why did you choose to split your time between academia and industry? This is from Brandon Horsley.
So the reason really, because I want to be able to build practical quantum computers, and without a company, that's not possible. In academia, you can do proof of principle experiments, but you cannot actually do the difficult engineering. You can't pay the bills for that either. Like, we work with foundries that charge an absolute fortune, and you could never, as an academic research group, engage like that. And so an academic research group can only produce proof of principle devices. So the company is a necessity in order to build practical quantum computers, also to do the right things. You know, you can't just go to investor and say, give me a lot of money. You're going to have a commercial model. You have to show that, you know, something will come back eventually. And so that's why you need a company. And that's why I'm in that company, because being in a company for me is important, because I need to, in a way, motivate the building of these machines and the components which we require. The 50% in the research group is because a lot of research can help in order to simplify some of the requirements in the hardware. So any achievement we do in the research group, where we just work with maybe 2 ions, can drastically simplify some of the hardware requirements we do in the company. And these actually work really, really well hand in hand. I'm very lucky my university has been very accommodating and made it possible for me to really do this kind of tandem. So that's not a straightforward thing, and I've been very lucky that is now a possibility. And so I think building practical quantum computers, for me, certainly having a foot in both entities is really, really helpful in making this happen.
Yeah, it's great. It's great to see that there can be this intersection between industry and academia, that they're not completely separate, that you choose one or the other, but there's actually this kind of merging of the. Yeah, thank you. So the last one is, can you guess what the role of platforms 1, 2, and 3 from the graph you showed?
Now, I can certainly guess that, but and I think from some of the things I've said in today, you've probably heard between the lines what is my belief. But again, like, you know, you're at a university, you should train critical thinking, and so I'm not going to say that. I refuse to answer that question, even though I believe you probably know the answer I would give. So there are some risky platforms. I'm not going to talk about 1 and 2. I'm gonna now talk about things like topological qubits, which is probably a number 3, and they're kind of really interesting because they're kind of really the essence of blue sky research. And so, in a way, I want to make a case. If I'm completely not in a platform 3, I believe I'm in a platform. No, I'm not going to say what I believe in platforms are, but a platform 3 also has some merit, because you're going to uncover some really beautiful blue sky research. So it's nothing wrong with being in a platform 3. Things like, I'm going to give you an example of what I believe is a platform 3 topological qubits. It's great that Microsoft is funding this. It's blue sky research at its best. Research councils don't even fund this. So it's fantastic, and we're going to get really interesting stuff out of that. So don't, in a way, discard platform 3s, but it might be just beautiful fundamental research. And blue sky research generates a lot of great stuff. So that's what I would say. But you must do your own rating of where you see a platform 1, a platform 2. There's plenty of data out there, and in a way, I would go more by what's demonstrated than what people promise you. That's the other thing. Like, you know, there is such a thing as interpolation, and you should use the previous data points. Gate fidelity is something. Get yourself a data point of where the gate fidelities have evolved, and just look at what has been passed and then draw a line in gate fidelity. Don't listen to people who say, about next year we're going to do all these things. I was in Australia in 2001 when people said, Bob Clark, who ran the effort at UNSW, then about next year we're gonna do that, and we all know it was next year, and even now 15 years later we're still not quite there what has been promised. But it doesn't in a way defeat the platform. Is not necessarily a bad thing for the platform. It just means there's some indication of how fast the platform moves, and you should just interpolate, look at the data which is out there, and then you can do your own rating.
Great, thank you. That's a great answer. We should draw our own conclusions, and yeah, that's perfect. Well, thank you very much for your talk, and I'm looking forward to hearing you again tomorrow for Universal Quantum. And yeah, thanks for joining us, and we'll see you tomorrow then.
Okay, thank you for having me.
Thank you. Bye.
Awesome. Bye-bye.